Example 2.4 is going to see us solve a separable differential equation which models a real-world example. We have 29 elk in the year 2024. And then 30 months later, we find that there are 37 elk. So the elk population is growing. And as long as we stay underneath 75 elk, there should be enough resources for a exponentially growing elk population. So this first part here says that if we can assume that the rate of growth of the elk population, so if I represent the population with P, then the derivative of P with respect to time, T, is directly proportional to the elk population itself, meaning it's equal to a constant times that population. Our second part asks us to find the general solution. So this is a separable differential equation. We have 1 over P times dP is equal to a K times a dt, which we can then integrate both sides and find that the natural log of the elk population, which will always be positive, I don't need the absolute value bars, is equal to K times T plus an arbitrary constant. In fact, that constant is going to provide detail based on our specific example. Solving this for the population, we put everything into the exponent of Euler's number, and we simplify just a little bit. That e to the c, if c is just a constant, then e to the c is just a constant. So I'm just going to rename that capital C. Cool. So our elk population equation as a function of time, right? Little t is over there. Everything else is just a constant, is equal to an arbitrary constant times e to the k t. All right, now let's use the initial value of 29 elk to give a specific solution. This is the general solution to this differential equation. I'll copy down our elk population equation. And using the fact that our initial population, when time is equal to 0, is supposed to be 29, we find that that C value is the initial population. So our population equation now looks like 29 times e to the k t. All right, let's use the second point to give more detail to figure out what this growth rate k is. If time is equal to 30, so I'm measuring little t in months now, my elk population is supposed to give me 37 elk. So 37 has to be 29 times e to the k t. Solving this, we get that k is equal to 1/30 times the natural log of 37 over 29, which we can estimate as 0.008121. Cool. So now our population equation with all the details is equal to the initial population of 29 times e to the k, which is 1/30 natural log 37 over 29 times t. And we can use our population equation to ask ourselves questions about the population. For instance, when will we run out of resources? So we could support exponential growth until the population reached 75. So let's set our population equal to 75 and then solve for when that's going to happen. 75 is equal to 29 times e to the k t. And skipping the algebra, pause the video if you'd like. T is equal to 30 times the natural log of 75 over 29 divided by the natural log of 37 over 29, which is about 117. or about 9.75 years, because little t was measured in months.